The last one is g of negative x. Yes. It's exactly the same. It's still negative x to the second power minus 10 times negative x and minus 3. Identical situation. So negative x squared, how much is that? Very good, because negative x times negative x is indeed x squared. Perfect. Excellent. And then? Yes, awesome. X squared plus 10x minus 3. Yes, if we want to write it as an ordered pair, we can. Okay. Any questions on how we evaluate functions? I would like us to look at domain and range for 90. And move on to 2.5. Okay, what do we see here? We see domain, anything from negative infinity to, oops, not 1, and then 1 to infinity. So as you see, this function is undefined at 1. Would you agree? Perfect. What about range? Imagine that you cut it with horizontal lines. Yes, 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 yes. No. No. This horizontal line does not cross the graph of the function. Yes, 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 yes. So what will you say about the domain? One more time. How do we write the domain of this function? So this is problem 90 on page 232. Domain is negative infinity to 1 with a parenthesis, union symbol, 1 to infinity. The parentheses say not 1. The bracket says including 1, but there is no bracket. The range says negative infinity to 0, union 0 to infinity, because 0 is not a y value for this function. This function does not have, there is no x that creates y 0. Any questions?
What does the actual function look like? What did it say? I can't read that.
I'm sorry?
I can't read what it says. It's so small.
You want to enlarge it?
Yeah. I guess what I'm asking is, what does the actual function look like? Like a 1 over x?
Oh, yes, of course it's a rational. Oh, yes, it's a rational function. It has, it's 1 over x minus 1, where the function is undefined at 1. Exactly. Very good. Okay, moving on. Okay. Let's look at a few basic functions or simple functions that you probably have seen at some point in time. So this is 2.5. Let's talk about basic functions. Why we're doing this? Because we want to eventually talk about transformations. Okay. But not yet. We want to talk about basic functions. Can anyone give us the simplest possible linear function? An example, which is the simplest possible linear function. F of x equals x. f of x equals x is the simplest possible function, and the graph is passing through the origin, bisecting the first and the third quadrants, always. That's a linear function, the simplest possible linear function. Quadratic. Quadratic function. Can anyone give us the simplest possible quadratic function? F of x equals, of course. That's the simplest possible quadratic function. And I'm sure you remember the graph of the simplest quadratic function is a parabola with a vertex at the origin. Here it is. F of x equals x squared. Any questions? Okay, next one. Simplest possible absolute value function. F of x equals the simplest possible absolute value function. It must be the absolute value of x. That's the simplest possible. Okay, let's graph it. It will bisect the first and the second quadrants. We also call it the v function. Next one, the simplest possible square root. F of x equals simplest possible square root function. F of x is the square root of x. Very good. Square root of x. Perfect. Let's graph it. Can anyone give us a domain of this function?
Should be from 0 to infinity, I think.
Indeed.
No positive.
Indeed. How come?
Because if you put a negative number in, you get an imaginary number.
Correct. Very good. So for the square root to exist, under the square root we have to have positive numbers or 0. So therefore x must be greater than or equal to 0, and here's the graph. This is the graph of f of x equals the square root of x. Good. Two more to review. Cube root function. Can anyone give us the simplest possible cube root? But the cube root. Just the cube root. The cube root of x. It happens that the domain of this function is all real numbers. So x can be any real number. Any even index like the square root, the fourth root, the sixth root has this problem. The numbers have to be positive or 0. But the cube root, the fifth root, the seventh root, very friendly function. Kind of looks similar to the square root, but not really, right? It's everywhere. So this is f of x equals the cube root of x. One last function. that I like to review is the cubic function. Not the cube root, but the cubic function. Can anyone give us the simplest possible cubic function?
F of x equals x cubed.
Exactly. F of x equals x cubed. Very important function, and here is its graph. So this is f of x equals x cubed. Please notice one thing. At 0, at the origin, the graph does not cross like this. It's a slow cross. Still only one x-intercept, of course, but it's a slow cross, not like this one. It makes a big difference, and you'll see later why. Okay, so we listed all these, and what are we doing with them? Why did we list them? And you'll see in a moment why we listed them and why we talked about that. So what I was going to show you is that we are not going to go through all the transformations except the horizontal stretching and shrinking. For some reason, they removed that. I saw it, but I don't see it right now. Omit shrinking and stretching graphs, which will be covered in 145. Okay, so we're going to look at everything except shrinking and stretching. They didn't say horizontal or vertical, so I'm assuming both. Okay, ready? So what's the idea here? We know these basic graphs. We want to analyze a function that is given to us to see how it was built from the basic functions. Why would I ever be interested in that? So I want to give you an example. Here's an example. Let's suppose you will do data analysis as an example. And you're going to measure, let's say, boys from the age of 0 months to 60 months. Or you are in the healthcare field and you want to look at a study, maybe collect data. And let's say you measure them from 0 months till 60, they measure their height, of course. And you're trying to fit the model. You want to fit a model, a function that will represent the real life situation we're looking at, heights of boys between 0 and 60. Which of the functions that we just listed you would think of applying here after you measure them and you put the points? So at 10, the average appears to be this, at 20, it happens to be this, at 60, the average height appears to be that. So we have these points, the average heights. Let's say we're looking at 100 people, 100 boys, and we come up with that. Yes, Maureen, sorry. Of course, of course. As long as we know those basic functions, of course we're going to fit a square root function. Some transformations on it, maybe shifted, maybe stretched, maybe moved up and down, but definitely a square root. You're not going to fit the absolute value, it doesn't look like it. You're not going to fit the square, x squared, doesn't look like it, and so on and so forth, right? It's the square root. Yes, Bob?
When you first look at the data, you couldn't assume, you couldn't guess and say it's linear. But then you'd be not accurate at the beginning.
Right, exactly.
But if you didn't have that part of the data, you might say, let me try to fill it in.
Right, but you have to, in this case, you have to measure from 0. Right. Perfect. Perfect example. Excellent. So now I'm going to come up with some functions, and we're going to analyze the transformations. Here are the transformations. I'm going to list all of them, and we're going to do this time only what they want. So my colleagues decided that. So there are three major transformations. Shifts, reflections, and the last group, shrinking or stretching. Stretching. You know I always run out of room. So shifts, reflections, shrinking or stretching. They told us not to talk about those. Fine, we're not going to. Shifts, two types. Vertical, horizontal. Reflections, two types. WRT, it's the lazy person with respect to. X-axis, Y-axis. And the last one, we'll leave it for the next class. But there are three major types. Shifts, reflections, shrinking or stretching. Vertical shifts, horizontal shifts, reflections with respect to the x-axis, and reflection with respect to the y-axis. Okay, so I'm going to start with shifts. So let's look at the following. Let's say I am creating a function, the absolute value of x minus 2, and the second function, g of x, the absolute value of x plus 4. They're not connected. I just want to look at them together, but they're not connected. So let's first discuss the function f. Which base function or basic function did I use to create f? Absolute value of x. Very good. So if we analyze this, then I used, of course, the base function or the basic function, the absolute value of x. When we graph the absolute value of x, as we just did, we know that it's a v function. It bisects the first and the second quadrants. And now the question is, where does this go? So notice one thing. First, we have to identify whether it's a transformation on x or a transformation on y. There is no transformation that does both at the same time. So first I have to identify whether I'm changing x or I'm changing y. And here's how I come up with the answer. Am I changing x or am I changing y? That number touches x. So I'm changing x. If I had the absolute value of x minus 2, the minus 2 would have not touched x, would have changed y. But this time, it's right there next to x. It touches x. The minus 2 touches x. Every time we change x, we expect something like this to happen. Every time we change y, we expect something like this to happen. Always. Since we're changing x, obviously this is a horizontal shift. But now we have to decide which side. I need to determine the x-intercept. I don't just memorize. If you subtract, we do this, we do the adding. So we need to find the x-intercept. The x-intercept of this function is the origin. Now the question is, the x-intercept of that function, will it be at 2 or will it be at negative 2? Careful, negative 2 minus 2 is negative 4. The absolute value is not 0. It will be at 2. Because when you plug in 2, 2 minus 2 is 0. The absolute value of 0 is 0. I don't want you to have to memorize this. Is that clear? Jay, is that clear?
Yeah.
So only 2 minus 2 gives us the x-intercept. The negative 2 minus 2 does not give us the x-intercept. So this is a horizontal shift of 2 to your right. 1, 2. This is it. Parallel to the other branches, to the other pieces. This is the absolute value of x minus 2. Now, obviously, the second one, where will that go? Find the x-intercept. And you will never forget where it goes. Where does x plus 4 in absolute value go? And the answer is to the left. To the left. We decided that this is only a transformation on x. The change touches x. If you compare the absolute value of x and the absolute value of x plus 4, you know the change is in x, not in y. Therefore, this is a horizontal shift. Horizontal shift 4 to the left. This one is a horizontal shift 2 to the right. This one has indeed the x-intercept at 2, and this one has indeed the x-intercept at -4. -4 plus 4 is 0. Another quick example here. Let's say f of x equals x plus 2 squared. Which base function or basic function did I use now? I used very good. I used x squared. Very good. So then now, this is x squared. Am I changing x or am I changing y? Compare. I'm not changing y. The change touches x. If you compare x and you compare x plus 2, the change touches x. If it touches x, then it has to be a horizontal shift. It's a different function. It doesn't matter. It's just a different function. Where does it go? Where will the x-intercept be?
Which side?
Yes. If I move it to the right, 2 plus 2 is not 0. Yes, it has to go to the left 2 units. This is x plus 2 squared. If I shift it horizontally, somewhere I have to have the x-intercept. If it's a horizontal shift, I'm looking for the x-intercept. If it's a vertical shift, it's a different story. But if it's a horizontal shift, and it is, because I'm changing x into x plus 2, I'm staying at the same height. The function stays at the same height. It just shifts to the left or to the right. Is that clear? Okay. Here's another example. F of x is the square root of x plus 2. And g of x is the square root of x minus 3. Two different functions, not connected. Don't look at both, just look at the first one. And please tell me the base function that I used this time. So if the base function is the square root of x, please analyze and tell me whether we are changing x or we're changing y. You understand that we're not changing x because the square root of x has no change. It's still the square root of x. The change is completely outside, does not touch x. If it doesn't touch x, it cannot be a change in x. Is that clear? So this is no change. See, nothing changed here, as opposed to this case. This is inside the function, right? This is not. I just copied the same thing. There's no change here whatsoever. The change is completely outside. It does not touch x.
So,
yes.
Hypothetically, if you put a 3 inside the radical, then it is changing x.
Yes, and we're gonna have a combo in a minute.
Okay.
Yes, but this is just one simple transformation. So when we graph the square root of x, as we know, we get this. How do I graph the square root of x plus 2? Up how many units?
2.
Exactly. It's a transformation on y. So everything shifts up 2 units. And this is the square root of x plus 2. Because by comparison, these two are identical. So this is an outside transformation, which is on y. Yes, please, Bob.
For some reason, that's a little easier to see than
Right.
than
I agree.
than the absolute
I agree
value.
because that kind of looks like reversed,
Yeah.
or the opposite that you would have expected. I agree. Very good. What about the last function here, g? What does function g do to the base function? So this is the orange function. Where do I shift to get this one? Down how many? Yes. 1, 2, 3. Exactly identical. So this is the square root of x minus 3. So this was a vertical shift. The first one was up to, vertical shift up to. This one is vertical shift down 3. And that completes this. We are looking at reflections now. Ready? So f of x, I said that I was going to do a combo. So let's do a combo before reflections, if you allow me. So I'm going to come back to reflections, because I promised. So let's say f of x equals x minus 1 squared plus 2. This function is created based on which base function, or simple function, in other words? What function did I use to create this? X squared. Perfect. Quadratic. Excellent. So now, in order of operations, just imagine that you are evaluating this function. You're not going to add 2 first. You can't do that. You have to evaluate the inside. Let's say you evaluate for x equals 4. 4 minus 1 squared, and then you add 2. So in order of operations, I have to perform the first operation, this, and then this. So you already told me that the base function is x squared. Excellent. First transformation is on x squared, but the second transformation is on 1. So what is the first transformation we have to perform on x squared? Careful. Careful, we cannot touch this yet. In order of operations, as if we evaluate. What does this do to x squared? Which one? Very good. First is x minus 1 squared, right 1. Excellent. The last one is x minus 1 squared plus 2, which is a transformation on this, not on this anymore. This transformation is on this. So now we compare these two and analyze and come up with, it's a transformation on x or a transformation on y. Compare these two and tell me what type of transformation is this. Exactly. Because x is the same. And now this is outside. So it goes up 2. So now, because we know this function, I know it looks silly, but I like to do this in all my classes. So I have x squared. You told me 1 to your right, correct? And then you said up 2. Can anyone give us the vertex? We haven't even graphed it, but we have the graph in our head. One more time, x squared. To your right 1, up 2. Can anyone give us the vertex?
That's 5.
Exactly. Can anyone give us the range? We have to start from the low.
2.
2, 2. We haven't even graphed it. Just because we know x squared. Say it again. Okay. Here it is. Look at my arms. Okay, we're going to graph it in a minute. I'm just trying to give you the perspective. Okay, so x squared to your right 1, up 2. So here's the graph. First we graph the base function, which is x squared. Then you told me to shift it 1 to your right. Here it is. So this is x minus 1 everything squared. The first one is x squared. And then you told me to shift it up 2. And that's exactly what I'm doing. 1, 2. Here it is. So this is x minus 1 squared plus 2. And you already gave me the vertex as being 1, 2. You already gave me the range 2, infinity. Excellent. That's the purpose of transformations. Having a deep insight of the function, an understanding of the function. That's all it is. So now we can go back. So this was a combo. It had 2 transformations. One was a shift to your right 1, and the other one was up 2. But that's the correct order of transformations. We shift to the right and then up 2. Great job. Okay, reflections. Here's my F, and here's my G. Not connected. Let's look at the first one. And please identify the base function first. Of course, very good. So the base or the simple function I used was the square root of x. The next step is where I have to identify whether it's a transformation on x or it's a transformation on y. Is it a transformation on x or a transformation on y? Square root is a square root. I didn't change the square root. So it cannot be a transformation on x. If the square root of x is identical with the square root of x, there is a change completely outside that has nothing to do with x and it does not touch x. If it doesn't touch x, it has to be a transformation on y.
That's a trick question.
The negative sign does not touch x. That's why I covered the same function here, the same function here. It cannot be a transformation on x. Clear? Good. So then, if it's not a transformation of x, and I know the graph of the square root of x, and there is a minus now outside of it, what happens? All positive values will change into, what transformation is this? With respect to the axis. Excellent. So when we graph the base function, here it is. This is the square root of x. And when I graph negative the square root of x, here it is. Very good. Final transformation. But I have to identify what changes. Because if I don't see what changes, I cannot come up with a correct transformation. So please compare this to this and tell me whether there is a transformation in x or in y.
The transformation is limited to x,
Say it again.
it's not the minus sign within the square.
So it would be a transformation on which one? X or y? Of course. The transformation touches x, which means from x, negative x, or from x, negative x. What transformation is that? With respect to? Exactly. Exactly. So look what happens now. Exactly. So this is a reflection WRT with respect to the y-axis. I'm changing x into negative x. But this one, I'm changing positive y into negative y. So this one is reflection with respect to the x-axis.